Whether you're gearing up for your engineering finals, FE or PE exams, or getting ready to teach an engineering course, thanks for dropping by during my office hours. Today, I would like to introduce you to one of fluid mechanics' core equations, the energy equation. The water-energy nexus describes the interconnection between water and energy resources, highlighting how the production and use of energy rely on water resources and vice versa. It emphasizes the significant impact each resource has on the availability, accessibility, and sustainability of the other. This relationship underscores the need for integrated management strategies to address challenges related to water and energy security, efficiency, and conservation. For example, energy production often requires substantial water resources, while water supply and treatment demand energy inputs. Managing these resources jointly is crucial for sustainability and minimizing environmental impacts. As one of the most fundamental equations in fluid mechanics, the energy equation is crucial for water supply and distribution systems as it helps calculate the energy required to move water through these systems. It aids in understanding factors like pressure, flow rates, and head losses in pipes, pumps, and other components. By using the energy equation, engineers can optimize the design and operation of water distribution systems to minimize energy consumption. It allows for the efficient sizing and placement of pumps, valves, and pipes, ensuring that water is transported effectively while minimizing unnecessary energy expenditure. Additionally, the energy equation helps identify areas where energy losses occur within the system, enabling engineers to make adjustments or improvements to reduce inefficiencies, lower operational costs, and enhance the overall sustainability of water supply and distribution networks. An energy equation is specific to an inlet section and an outlet section, as well as the energy gains and losses in between of these two sections. Given gammas as the specific weight of the fluid, the P1 over gamma and P2 over gamma terms are named pressure head. They are related to the pressure energy added to the fluid at the inlet section, section 1, or at the outlet section, section 2. The Z1 and Z2 terms are called elevation head. They are the potential energy of the fluid due to its elevation above a reference level called datum. The next two, called velocity head, are related to the kinetic energy of the fluid. In these terms, g is the gravitational acceleration. The alpha-1 and alpha-2 are kinetic energy correction factors, defined as the ratio of kinetic energy based on the actual velocity of the fluid to the kinetic energy based on the average velocity of the flow, considering that most flows are not uniform in the real world. Typically, a fully developed laminar flow in circular pipes corresponds to an alpha value of 2, whereas for a turbulent pipe flow, alpha is usually between 1.04 to 1.11. Especially if information on the velocity profile is unknown, it is a common practice to take the kinetic energy correction factor as 1 for a turbulent flow. Summing up pressure head, elevation head, and velocity head at section 1 altogether derives the total head at section 1. This is the total energy conserved in the flow at the inlet section. This initial energy is subject to increases and decreases as the fluid flows through the pipeline, passing through pumps and turbines if any. Summing up pressure head, elevation head and velocity head at section 2 altogether derives the total head at section 2. This is the total energy remaining in the flow at the outlet section. Therefore, the total heads at the inlet and outlet sections remark the energies conserved in the flow at these two locations, regardless of whatever happens in between. HP is called pump head. If a pump is present in the system, pump head represents the energy this pump can provide to the flow. For the flow, pump is an energy-adding device. In other words, the flow gains energy as it passes through the pump. We'll delve into the specifics of pump head in a separate video discussion. HT is called turbine head. If a turbine is present in the system, turbine head reflects the energy the flow loses to the turbine. As an energy-consuming device for the flow, turbines convert the flow's mechanical energy to either another form of mechanical energy such as windmills, or the mechanical energy in the flow can be harvested to generate electricity in a magnetic field according to the Ampere's circuital law in classical electromagnetism. Turbines are uncommon in water supply and distribution systems, as they reduce energy from the flow. The last term in the energy equation is called head loss. Head loss, as the name suggests, indicates energy losses in the flow. There are two types of head loss. 1. Major head loss, also known as pipe head loss. It occurs all along the pipeline, mainly due to the viscous effects of the fluid and the dissipation of energy in the form of heat. 2. Minor head loss, also known as component head loss. This type of head loss only occurs when the fluid passes through components such as valves, fittings, bends, tees, or heated channels. Although such losses are termed minor losses, they often account for a major portion of the head loss due to the complexity of the piping system and the number of fittings that are used. For relatively short pipe systems, with a relatively large number of bends and fittings, minor losses can easily exceed major losses, especially with a partially closed valve that can cause a greater pressure loss than a long pipe. When a valve is closed or nearly closed, the minor loss is infinite. Head loss holds significant importance in fluid mechanics, and this topic will be covered extensively across multiple sessions and separate videos. Now that we have talked about each of the 9 terms in a typical energy equation, let's take a look at this equation again. The energy equation is often provided in textbooks in the form shown here. However, this form does not facilitate our understanding of the equation. How about we imagine we are the fluid passing through the pipeline from section 1 to section 2. Starting at the inlet section, the energy we have is the total head at section 1. After passing through the pump, an additional energy HP is added to the flow. So we add HP to the total head at section 1. If there is also a turbine, after passing through the turbine, we will lose energy HT to the turbine. So subtracting HT. Now remember that we are losing energy all along the way due to major head loss, or pipe head loss. And we are losing energy in the form of minor head loss or component head loss each time there is a device installed in the system. Hence, we must subtract the total head loss, HL. When we finally arrive at the outlet section, the total head at this section equals to the remaining energy in the flow. Until now, we have completed the writing of energy equation by following the initial status of energy in the flow and tracking the energy gains and losses along the pipeline. We can easily rewrite the equation to remove all the negative symbols. So, the energy equation becomes our familiar form. Thank you for tuning into this video. If you have any questions or specific civil engineering topics you'd like me to cover in future videos, feel free to leave a comment below. Your likes and subscriptions motivate me to create more content, ensuring you don't miss out on future updates.